This is part 3 of our video series looking at Bayesian statistical analysis in SPSS. In this section we're going to be looking at parameter estimation Bayesian style and also the Bayesian equivalent of a frequentist hypothesis test. Now to begin with, we're going to look at parameter estimation and introduce the idea of credible intervals. In the previous example we introduced the fundamental principles of Bayesian analysis using Bayes' theorem. And in particular, we saw how Bayes' theorem can combine evidence from new data, which we call the likelihood, and prior probabilities to provide a posterior probability. Now, a probability could be a parameter value that we estimate, just in the same way that a mean or a median might be a parameter value that we estimate. So in a similar way, we can use Bayesian analysis to estimate population parameters. Bear in mind that population parameters include not just means and proportions, but also things like, say, the difference between two means, maybe the mean blood pressure for left-handed people and the mean blood pressure for right-handed people, the proportional differences, the percentage difference in voting habits of two groups of people with different ethnicities, or maybe even a correlation value, a correlation coefficient, let's say between travel distance and frequency of shopping at a particular store. Now, just as we used Bayes' theorem to estimate a posterior probability by combining our evidence with a prior probability, when we're estimating our parameters such as, say, the difference between two means, what we're really doing is estimating a posterior distribution, showing a range of values within which the parameter is likely to lie. So our prior takes the form of a distribution as well, about which we normally provide some sort of information, such as the anticipated mean and variance. In Bayesian analysis, we're estimating a parameter's posterior distribution by combining our prior distribution information with the likelihood obtained from the data. So specifying a prior distribution is an important aspect of this process. Now, Bayesian analysis will often return a mean estimate of the parameter value, such as the mean difference or the mean correlation, but really, as Bayesian analysis sees the parameter as a distribution of values reflecting uncertainty, researchers tend to focus on what are called the credible intervals that encapsulate 95% of this distribution. Credible intervals are the Bayesian equivalent of the frequentist confidence intervals, except that here we can say there's a 95% probability that the parameter lies within these bounds. Now, if credible intervals estimated a range of values that related to some sort of difference between groups, think about what this would mean if the lower interval was a minus number and the upper interval was positive. So for example, in the SPSS output below, we can see that the mean difference between the previous experience of clerical workers and managers using Bayesian analysis is about minus 7.42. That's basically just the difference between an average of 85 months of previous experience for clerical workers and 77 months for the managers. Although the overall estimate's minus 7.42, the credible intervals here indicate that the actual value could range between minus 26.1, where clerical workers have actually an average of 26 more months than managers, to 11.26, where managers could have 11.26 more months than clerical workers. In other words, there's not much evidence that one group has more previous experience than the other. We would therefore conclude that when it comes to estimating the parameter value of what's the difference between the average number of months worked by clerical workers and managers workers, that there's a great deal of uncertainty and that it could be positive, it could be negative, or it could in fact be zero. Okay, let's turn our attention to the equivalent of a hypothesis test and introduce the concept of Bayes factor. In the world of statistical inference, there is of course an important difference between estimating a population parameter, just as we've been doing, and testing hypotheses about it, where we're trying to make statements about whether or not something is likely to be true. They are separate things. In the previous example, of course, we looked at how Bayesian estimations attempt to approximate a parameter's posterior distribution, but now we turn our attention to testing hypotheses using something called Bayes factor. This is, I guess, the equivalent of a frequentist p-value. Now, in the frequentist universe, their approach to inference is to really focus on what's called the null hypothesis, the statement that nothing's going on, there's no difference between the groups, etc. And when a p-value is calculated and found to be lower than some sort of pre-specified level, usually referred to as an alpha level, the convention usually being something like 0.05, sometimes 0.01, meaning 5% and 1%. When that value falls below that threshold, the convention is to reject the null hypothesis. But what we can't do with this information is use it to accept the alternative hypothesis. The test simply doesn't consider that type of condition. It's very one-directional. So what happens when the result is non-significant, such as when the value is higher than 0.05? If you get a p-value like 0.38, 38%, all that happens is that the null hypothesis is not rejected. As such, the frequentist approach has very little to say about evidence for one hypothesis versus another, whereas a p-value is used to reject or not reject a null hypothesis. Something like a Bayes factor compares the evidence for separate hypotheses by dividing one by the other. In SPSS, the resultant ratio of evidence attempts to quantify how much more evidence there is for the null hypothesis versus the alternative hypothesis. And by doing so, it's comparing evidence for both hypotheses, which is something that a frequentist p-value does not do. So in the Bayesian universe, analysts use Bayes factors, often labeled as B, as the equivalent of a p-value to make a statement about whether or not something is true, whether or not a hypothesis can be supported. And really, these are simple ratios that compare the evidence for the alternative hypothesis and the evidence for the null hypothesis. So for example, a Bayes factor comparing a null hypothesis to the alternative hypothesis would show that the data are b times more likely under the null than under the alternative. And because it's a ratio, it can range from 0 to infinity. But the value of 1 would indicate that there is exactly the same evidence for the null hypothesis as there would be for the alternative hypothesis. So 1's kind of the reference point that we tend to compare things against. That's the bit we're saying there's no more evidence for one hypothesis versus the other. Values greater than 1 in this case would indicate increasing evidence for one theory over the other. So for example, the null over the alternative hypothesis. And values less than 1, the opposite, increasing evidence for the alternative over the null hypothesis. Now, Bayes factors with the label BF subscript 10, if you like, refer to situations where evidence for the alternative hypothesis is divided by evidence for the null hypothesis. And in such situations, larger values indicate more evidence for the alternative hypothesis. Sometimes you're going to see a Bayes factors with the label BF subscript 01, which refer to situations where it's actually the opposite, where evidence for the null hypothesis is divided by evidence for the alternative hypothesis. In such situations, larger values indicate more evidence for the null hypothesis. This is the convention that SPSS uses, certainly when it's comparing, for example, averages in the Bayesian equivalent of an independent samples t-test. And we can see here it gives us a little table in the help system where it says, look, if you're getting values, say, in the range of 10 to 30, that indicates really strong evidence for H0, which is the null hypothesis. If you're getting values in the 3 to 10 range, then that's kind of moderate evidence for the null hypothesis. And if it's kind of quite small values where the ratio is 1 to 3, they're saying that's anecdotal evidence for the null hypothesis. So a value of 2 would actually indicate that the null hypothesis is twice as likely as the alternative hypothesis. And then we have, of course, a value of 1 indicating no evidence either way. And then we have a value of 1 divided by 3. So it's kind of like 1 to a third, if you like. And that's called anecdotal evidence for the alternative hypothesis. And then a third to a tenth, so 0.33 to 0.1 is moderate evidence for our hypothesis. So the smaller numbers, when you get into fractional numbers, when you get into little decimal places, it's starting to indicate more evidence for the alternative hypothesis than there is for the null hypothesis. You should bear in mind, however, that when you look at other systems, the direction of interpretation may go in the opposite direction, where they're using the BF subscript 10 as opposed to BF subscript 01. So they're just dividing the alternative by the null rather than the null by the alternative. So bear that in mind. In SPSS, larger Bayes factor values indicate more evidence for the null hypothesis. It should be noted that in other analytical programs, the opposite interpretation is made. In the above a table from the help system, it's provided to give users some guidance as to how to interpret the Bayes factor and the strength of evidence for the null H0 versus the alternative H1 hypotheses. And just to show you what that would look like, using the same analytical examples before, we can see that based on the previous table, the resultant Bayes factor is 8.441, which is down here. It provides moderate evidence for the null hypothesis that there's no difference in the average amount of previous experience for clerical and managerial workers. Now, we need to be clear what we mean by moderate evidence for the null hypothesis. What we're actually saying here is that you are 8.44 times more likely to get that data, to get a difference as large or as small as the one observed, if the null hypothesis is true than if the alternative hypothesis is true. So what we're not saying is, we're not saying that the null hypothesis is 8.44 times more likely to be true than the alternative. We're saying that the data is 8.44 times more likely to occur under the null hypothesis than the alternative hypothesis.